Hello and welcome to the next installment of our Saratech Enablement series. My name is Monique Anderson. I'm the Marketing Coordinator at Saratech and I will be your host today. Presenting today we have Mark Anderson, who is an application engineer here at Saratech, and he'll be teaching us about additive manufacturing with NX. But first, I want to tell you a little bit about the Saratech Enablement series that we've had great success with. We usually run about 30 to 45 minutes and our training is always led by subject matter experts. We cover topics including FEMAP, NX, Solid Edge, Team Center, and much more. So be sure to check out our website for dates and times, which may vary in the coming months due to customer feedback. Our goal for the Saratech Enablement series is to help you get the most out of your software, to share knowledge amongst each other, and to build a community of users that will help empower each other. As always, this is an open forum, and we look forward to you participating in the training. If you have any questions or comments during the presentation, please type them in the chat box and I'll kindly interrupt Mark and let him know your comments and questions. And with that, I will pass the baton to Mark. Thanks.
Hello, my name is Mark Anderson. As Monique said, I'm an applications engineer with Saratech. Today we're going to be going over additive manufacturing. What is it? How does it differ from traditional manufacturing processes? What are the new geometry creation tools that NX has implemented that allow you to create these new features? And they have generally been outside of our manufacturing capabilities. We're also going to take a look at tools available in NX for modeling the additive and subtractive features. We're going to take a look at printers that are supported by NX out of the box. And then we're going to take a look at the 3D nesting ability within the 3D build tray or the printable area inside of NX. So what is limiting our potential? Is it our performance, design complexity, weight of the part, material properties? These are all difficulties that we run into between design and manufacturing. There's always been a disconnect between what we can design and what we can manufacture. So additive unlocks the next frontier of possibilities. It transforms the thinking from conventional to an additive style of mentality. And with the additive style mentality, you can get parts that are more streamlined, ergonomic. The topology optimization gives you the ability to produce parts that they have in mind different factors when you're starting your design, whether that be forces, loads, tolerancing, etc. So the next frontier in performance, we have our products. We have 10 times faster development time, 100 times faster design changes, and then we can optimize our designs for reduced weight, increased strength, improved serviceability. Our materials, we have limitless control. We automate composites for multi-axis robotic printing, multi-material parts in a single part, and then microstructures that tune material properties. We have limitless agility, zero cost for the greater complexity. We have a one-piece lot size that you don't run into the prototyping issue that you have in today's market, where if you had to create one part, it's going to be very, very costly. You print one part, it's no different than printing 5 parts. And limitless opportunity, zero inventory, you produce parts on demand, and everything is customizable. Here's our traditional thinking and our streamlined process. We have our conventional thinking, multiple data conversions. You have uncontrolled workflow from your printing preparation software, and you have a disconnected software for your production software. And then how do you certify that part after it came off of these different disconnected items? And we're going to show you in NX how we bring all this together inside of one module. So we always use the smart model-driven process. We start with our master model, and then that master model drives all processes downstream. Initially, you have your design, then you simulate to make sure that you have all your different critical requirements in place, and then you print. You have data management and shop floor connectivity, and then we have our Siemens production software and the MES systems, and all of our partnerships with our printers, printer manufacturers. So we're going to look at design first. We can reimagine our products. We have new convergent modeling, which is a facet modeling technique. You generate design using the topology optimization. You can introduce lattice structures inside of hollow parts, and you can design rules for manufacturability. So design for additive manufacturing, the traditional versus the new mentality of thinking. Your traditional prototyping, you design it, you prepare it, and then you make it. If you have any type of modifications that need to take place, this process starts over and it continues and starts over and continues. So now with additive, we can scan to print, we simulate, we can modify the part, then make the part. But now we have our optimization tools. We can design our part, optimize the part, validate the part, and then make the part, and ensure that all of our design intent is in the part. All of our loads, our structures are what they need to be for the design of that component. Convergent modeling technology, it works directly with faceted surfaces and solids. It's unlimited flexibility to design innovative products, and there's no need for reverse engineering. So this is a convergent modeling technology. It's designed without conversion, 10 times faster than all traditional methods. And you can use this convergent modeling directly inside of NX and use the tools, whether it be CAD or CAM, to work directly off those faceted models. This is a small video demonstration of how they're going to optimize these features. It's going to give you a much more streamlined part. It's going to take into consideration loads and strengths. And what they're going to do is they're going to create a cage at this region. And you can see that they're just using the synchronous technology, the handles to push and pull their features, creating this drive line of where they want this cage to be located at. And once they develop this, it's a simple operation inside of NX to develop that cage. Now that cage is on top of the part. It's not united with the part. So further down the model, once they get this cage how they want it, then they would unite the model and it would become one component. And this is just showing the topology optimization tools inside of NX. So topology optimization, it's all operations inside of NX can utilize the topology optimization. You can do multiple load cases, and then you can optimize the model. It can be refined with the convergent modeling tools. And in the picture, you can see that the original designed component, it's bulky, it's square, it's very prismatic. And using the topology optimization, all the loads and strengths were taken into consideration, and it gave it a much more streamlined shape. It's reduced weight, but it still contains the same structural strength and integrity that it must have for that component. This is a small video on how they're going to optimize this front piece here. They're taking into consideration the optimization features. And these are just different features inside of NX that are controlling the topology optimization. So they're showing the component inside of a bounding block. They're showing loads, which direction the loads are going to be at. They're applying these, and then it's going to show whether it's valid or if it is not valid, or if it must be altered. And this would be your end shape after the optimization. The lattice structures, you can design lightweight components that still maintain structural integrity, but you can create hollow structures and produce a lattice inside of that for strength and rigidity. You can lightweight components for structural integrity, integrated lattice for structural development, and complex geometry represented as facets. Now this is a video. This operation, it's not introduced in version 11 yet. This will be introduced in version 12 for the lattice structure. So this is just a small preview of what will be available very soon. And you can see it's just the same NX dialogues as we've always been used to seeing. And they've shown a small model created. They're picking the outside surfaces that they're wanting to hollow. And then they're going to tell it the different lattice structure that they want. And once they create this, it'll show you the internal lattice structure of that boss. And they're doing that for the lightweight structure. It will maintain the strength and integrity of the part, but it will give you the ability to reduce weight. Now we can also input design rules, ensure the part manufacturability, avoid costly redesigns when a part is designed and found out to be inadequate during the manufacturing. So what this is doing inside of Checkmate is we're validating this part. We're validating that the part meets all of our criteria for the design intent of that component. If the design intent fails, we'll be able to see this in a report that's out of checkmate, just like we've always seen with our CSE tools. So now they're analyzing this part. It's recognizing regions that require support and loads. It's showing those loads in red, the direction of those loads. It's identifying enclosed voids where lattice structures would be. And it's giving us the same dialogues as checkmate always has given us. It's giving us different views, different information windows for what we're asking it to check. So now with our smart model driven process, we're going to go to the 3D print section. I'm sorry, simulation section. We're going to simulate this part to make sure that all of our predictive performance can be achieved. We're going to optimize the part design with the advanced analysis tools. We're going to validate the product performance. Then we're going to simulate the additive process, the printing process. And we can do all of this inside of NX software, so we don't ever have to do this in real life and have to redesign. So we're taking away a large portion of the design of today's day and age. Traditionally, we'd have to create these parts to find out that they were not going to be adequate for the design purpose. Now we can simulate these and get it right out of the beginning instead of having to do it later. So we have our topology optimization, our design for additive manufacturing using convergent modeling. We can validate for additive manufacturing. Then we can come back to design for AM if we need to, or we can continue on, validate for AM for the performance, and we can continue back to design for additive manufacturing if need be. It's a multi-scale approach, all inside of the software and not the hardware. So the topology optimization for analysis, objectives and constraints at a global level, multiple solutions in the same optimization, and optimization of components within an assembly. So you can do multiple checks at the same time on the same part. You can do assemblies. These are all the tools that are available inside of checkmate for the topology optimization. Now we're going into the 3D print section. We have multiple types of printers. We have powder bed fusions, multi-jet printers, hybrid additives, where it's an additive subtractive machine, and then we have multi-axis fused deposition, where it's using a robot inside of a robotic platform to depose the material. It gives you a much larger work envelope, and it's not an individual singular machine. So the powder bed fusion technology is the most widely utilized metal additive manufacturing technology out there. It's the most used. You can print fine internal details and complex features, and you can get near forged part material properties, which is very important. The powder bed fusion design model, you select your 3D printer, you position the nested parts on the build tray, you create your support structures if necessary, you define the build process, then you verify the laser's toolpath, and then you drive the 3D printer to your printed part. Now, additive manufacturing for metal parts within NX, we can produce the next generation designs with the powder bed fusion. And this is the basic property, basic principle. You select your printer, you get the build tray, that's your build volume, then you're going to add components. And I'm going to be showing this same demo here later on in a different printer so that I can show the 3D nesting capabilities. Once you do this, you make sure that it fits inside of the build tray. Then you generate your code, and then you can view your slices. Your post-printing finishing, integrated NX CAM, they produce high-quality parts within a precise toolpaths, automate NC programming, program any part using a wide range of capabilities, and it's all inside of one system, NX software. Now the multi-jet fusion machines, you print plastic parts using a process similar to inkjet printing, make parts with high dimensional accuracy and improved properties, and it builds parts 10 times faster. And that's for the plastic side of parts. For your multi-jet fusion, the process remains the same. You select your build tray, add your components, automatically nest the parts, you define or adjust your process, and then you drive the multi-jet fusion part to build your printed parts. Now, additive manufacturing of plastic parts within an NX using the HP Fusion, Jet Fusion 3D printers. We also have the hybrid additive manufacturing, and it combines 3D printing with CNC technology on one machine. Complex, large size parts with internal cavities, and you can eliminate the support structures. One machine is the Lasertech 65 Morisiki machine. but there has been a few other machines that have came out that have the additive subtractive capabilities inside of one machine. And I believe that this is going to be the wave of the future. Parts are going to be made on these types of machines as the cost gets decreased. And every shop is going to have something like this, because you're going to have something like this to keep up with the marketplace. This is the LaserTech 65 machine, and it's going to show you the hybrid process. You have different operations inside of NX that creates additive or subtractive operations. This is an additive operation. It's building the part up from a build plate, and it's blowing out powdered metal through a laser that's sintering it on contact. We've just been able to get a lot of aircraft parts that have been certified to be manufactured with these processes. And the example on the right, it shows a marine industry example. It's a propeller, and that went from 6 to 8 weeks to manufacture it to 36 hours. With that type of increase in efficiencies, you can't produce this part any other way and stay in business. So we're going to see more and more of these style machines out in the marketplace as the cost is reduced. It's just like everything out there in the world. The newer the technology, the more expensive it is, the more common it becomes, the less it costs. And when we see that is when we will see more in the marketplace. The multi-axis fused deposition modeling, you build composite parts with various sizes. We leverage robots, flexibility to print parts of any complexity. All of the robots have 7 axes to them, and then we can put different heads on them for the deposition processes. And we can also eliminate the support structures using this methodology. So the Stratus, this is just an integrated Stratus advanced extrusion technology. It's the Siemens MC industrial motion platform and the Siemens PLM designs product to product workflow. And it's using the robotic KUKA robot to do the additive process. So now that we went through the smart model driven process, we've done design, simulate, 3D print, and partnerships. These are the different partnerships that we have with the additive manufacturing industry. We have partnered with Trump, EOS, DMG Mori, HP, Stratus, and Materialize. These are all printers or machine builders that we've partnered with to be able to program those machines out of NX out of the box with no special add-ins. This is a smart driven additive manufacturing workflow. You have your initial design, your design space, optimize, adapt the design, validate, prepare for printing, finish and inspect, and then you have your final part. And this is the workflow for the smart model driven additive manufacturing. Now, before I get into the summary, I'll go through the 3D build process for you. So what we'll do is we'll start off with opening a part. We'll make sure that we are in the additive expert role. Then we're going to go into the additive module. We're going to choose a file new. We'll choose an empty build tray. Select 3D printer. We're going to select a 3MF file printer. And it shows our build tray. This is our volume of that machine. We're going to add a component. We have our component here. We'll go ahead and add this. So now it's put it on the absolute 0 location of the machine and the part. So now there's 2 ways of doing this. One way would have been when we add a component, we can go in here and we can say pattern after add, and we could pattern the component for as many components as we need in that build tray, or we can add it and then we can do pattern component. We'll select the component. I want to tell it a count of 20 pieces, count and pitch, and a pitch distance of 5 millimeters apart. Now I want to select a vector. We'll use the Z-axis vector. So now it's going to give me 20 instances of that part. And it doesn't give you a wheel spinning or anything like that in this dialog box, but it is working in the background. So once it gives us this pattern, you'll see 20 components stacked on top of one another. To do this 3D nesting, you don't have to keep them inside of the 3D the build tray area. They can be anywhere on the screen. And once you have the instances, you see we have our 20 parts. We're going to go right click on File Printer, Automatic Nest, and here's our nesting parameters. Distance between parts. It will give us the adequate distance and minimum distance that it can have these 20 components apart from one another and stay inside of the build tray. If we tried to change this, it would say we have distance between parts is too small. So this, now we're going to tell it the constraints. We could fix the positions if we wanted to, fix rotation, or we can allow it to be free. View in progress is going to show us the different manipulations. In the settings, we have optimize height, distribute height, optimize slice volume, optimize height and slice volume. I like to choose optimize slice volume. The accuracy is going to be 2.5 millimeters. So at any given moment, it can be plus or minus 2.5 millimeters of that 14.6077. And then it's going to run the algorithm for 1 minute to organize these parts in the build tray before stopping. So once I click OK, the progress bar on the bottom will start to show that it's running through the algorithm. It's placing the parts in position in the build tray, and it's giving it as many times as it can in 1 minute. It's looking at different positions that it can produce these parts. Once it finds a very close match of where these parts can be positioned, you'll see them start to rotate around on the screen. And you can see my create nesting, my progress bar is at 30% on the bottom left-hand corner. Now you can see that it's flowing the parts around freely inside of that build tray to get all 20 parts inside the build tray and organized to those parameters. And then once it stops, this is now our build tray with our 20 components in it. And that is our 3D nesting algorithm. So our summary, NX has several built-in additive and manufacturing, additive and subtractive design tools, topology analysis, the lattice tools, highly specialized simulation tools that will show the build process, analyze the geometry to give a lighter, more robust design, build net shape geometry easily, multiple machine tools are supported, and you have many material choices to be used. Our next session is going to be design for additive manufacturing. That's the precursor to this demonstration. And it's going to be with Siemens NX and HP Multijet Fusion 3D printers. This will be Tuesday, December 12th, 2017 at 11 a.m. Pacific Standard Time. And presenters will be Siemens PLM, Forecast 3D, and Saratech. Ready to take it to the next level? Saratech provides hands-on training classes for software users of all levels. We also provide engineering services to address your demands for advanced engineering capabilities, whether that be design, manufacturing, CAM programming, or CSE tools. We offer all of those services. And I thank you for attending. And if you have any questions, I will open it up for questions at this time.
Awesome. Thank you so much, Mark. Great presentation today. And to all our attendees, we will be posting this video to YouTube later today, so feel free to pass along to your friends and colleagues, and please be sure to subscribe to our channel. Follow us on Twitter and LinkedIn for upcoming dates and topics. And please don't forget to stick around for about 10 seconds after. Fill out our survey, let us know how we did and what you liked. And thank you so much for attending, everyone. Have a great rest of your day.
Thank you, Monique.